Hello everyone, I am Jisha from the Department of Artificial Intelligence and Data Science at Savita Engineering College. Today I am going to present a fundamental topic in linear algebra that plays a vital role in both theoretical and practical aspects of data science, numerical analysis, and machine learning. This method is known as QR decomposition. This presentation will cover an introduction to what QR decomposition is, its application in real world and computational problems, a complete explanation of a Python program that performs QR decomposition using the gram schemate process, and a walkthrough of sample inputs and how we get the expected outputs. Let's begin by understanding what QR decomposition is all about. QR decomposition is a method of decomposing a matrix into an orthogonal matrix Q and an upper triangular matrix R. This method is widely used in solving systems of linear equations, eigenvalue problems, and least square fitting. Given a matrix A, QR decomposition finds two matrices Q and R such that A equal to Q into R. Q is an orthogonal matrix, its columns are orthonormal vectors, and R is an upper triangular matrix. If A is an M into N matrix, then Q is M into M matrix and R is M into N matrix. The applications of QR decomposition is the QR factorization is one of these matrix factorizations that is very useful and has very important application in data science, statistics, and data analysis. The main applications are solving linear systems of equations, eigenvalue computation using the QR algorithm, least square method in regression, principal component analysis, and signal processing and control systems. Let us now look at the Python code used to implement QR decomposition using the gram schemate process. This process constructs an orthonormal set of vectors from the columns of matrix A. Let's go through QR decomposition Python code line by line. Import numpy as np. First, we have to import the numpy library, which is essential for handling arrays and performing numerical operations like matrix multiplication and finding vector norms. The second line is def QR underscore decomposition A. We define a function named QR decomposition that takes a matrix A as input. This matrix will be decomposed into Q orthogonal matrix and R upper triangular matrix. And the next line is n comma m equal to A dot shape. We get the dimensions of matrix A. N is the number of rows and m is the number of columns. Next line is Q equal to np dot empty n comma n, U equal to np dot empty n comma n. We create two empty matrices. Q will eventually store the orthonormal vectors. U will store the intermediate vectors in the gram schemate process. And the next line is U all rows 0 columns equal to A all rows 0 columns. The next line is Q all row 0 columns equal to U all row 0 columns divided by np dot li and lin alg dot norm U all rows 0 columns. Take the first column of A. The first line shows that take the first column of A and store it in U all rows 0 columns. Normalize it, that is divide by its norm to get the first column of Q. And the next line is for I in range 1, n. Start a loop to compute the remaining columns of Q from 1 to n minus 1. And the next line is U all rows I columns equal to A all rows I columns. Explanation is we initialize the current column of U with the corresponding column from A. The next line is for J in range of I, U all rows I columns minus equal to A all rows I at Q all rows J into Q all rows J, which means this is the gram schemate orthogonalization step. For all previous Q vectors, we project A all rows I onto Q all rows J columns and subtract that component from U all rows I columns to make it orthogonal. The next line is q all rows comma I columns equal to u all rows comma I column divided by np dot linalg dot norm, that is q all rows comma I column. The explanation of this code is we normalize the orthogonalized vector u all rows comma I columns to get the ith column of the q. The next line is or equal to np dot zeros n comma m. We initialize matrix or as a zero matrix of size n into m. Next we have I loop and j loop. Now we compute R using the dot product between the column of A and Q. At is nothing but it is a dot product. Because R is an upper triangular matrix, we only compute when J greater than or equal to I. And next we are going to print the orthonormal matrix Q and the upper triangular matrix R. Next line shows that the A equal to np dot array eval input and QR decomposition A. The user inputs a matrix and eval input evaluates the string into a Python list. This list is converted into a numpy array and passed to the QR decomposition function. The input is provided to check whether the code is correct, and QR decomposition is a powerful technique used in solving linear systems, least square problems and eigenvalues computations. We implemented it using the Gram schematic process. We calculated both Q and R using NumPy. This method is foundational in numerical linear algebra and is widely used in fields like machine learning, statistics and scientific computing. Thank you.